Thank you. The topics I will cover in my talks are a bit maybe far for the moment from the topics of ADS-CFT problems. Although a correlation function, I hope, will be in the next future for all these ADS-CFT problems. But okay, for the moment, of course, you are still looking at the spectrum, and a lot of problems are still to be solved there, related to beta ansatz and so on. But of course, from integrable models point of view, the problem of correlation function has been around for very long, because as soon as you want to enter applications, for example, to condensed matter, it's very important to go beyond the spectrum to really address the problem of dynamics, and in fact really to compute quantities that can be eventually measured experimentally in systems which are described like magnetic systems for spin chains by such integrable models. And in fact, when you consider this problem of correlation functions, there is, say, a lot of goals there that you can address, of course, but there is two for me when I entered this game, two goals that were quite obvious. First goal is, can we compute something in practice? Can we compute some really correlation function and eventually compare to experiments? Because there is many experiments in condensed matter that where there is a lot of data, and can we compute in practice something and compare really to experiments? So this is one question. Another question is more, say, theoretical, more fundamental in some sense, is we know that a lot of these integrable models, when you go to the, even if they are defined on the lattice, when you go to the thermodynamic limit and when you go to the continuum limit, they are believed to be described by conformal field theory. However, direct check of that is available only for Ising model case, right? Where we can compute really on the lattice everything, take the continuum limit and check that you get the proper critical exponents that are predicted by the corresponding conformal field theory. If you take just XXZ spin chain, and we know that it should be also described in the disordered regime, where you have gapless case by conformal field theory, there is only indirect connection to conformal field theory, which is simply using the fact that if you are in a finite geometry, you have a correspondence between central charge and the finite size corrections. So the goal here would be to really compute correlation function from the lattice model and to check explicitly on the correlation functions that you get the proper critical exponents that are really predicted by conformal field theory. Okay, so I will try to at least discuss these two problems in my talk, and also I will take the opportunity of this talk to not only to address this problem, but to introduce few tools that we have designed along the years to attack such problems, and that hopefully could be useful in other contexts, maybe in ADS-CFT sometimes. Okay, so let me start with a specific model. As I said, the problem of correlation functions in these integrable models is quite complicated, and we don't know the general way to address this problem. So since we don't know the general way, we stick to a specific example, which was already historically very important, and where all the main techniques that we know have been invented. So this is the Heisenberg spin chain. So several people already have talked about this today with nice introduction this morning. So I will not spend too much time on the history, but let me just remind that this was invented in 1928 by Heisenberg, and in fact it's rather funny why this model was designed, because just 3 years before there was the Ising model which was invented, and unfortunately Ising was solving the first one-dimensional case, and there is no phase transition. And so, since there was no phase transition, and he was looking for that, of course, for this Curie point and so on, and he concluded wrongly that there was no phase transition for the higher cases, and so he just gave up. And that's why Heisenberg came with a more sophisticated and much more complicated model, because it's not free fermions, it's really an interacting case, to tackle this problem of magnetism. While ultimately, Onsager solved a two-dimensional case, and there is phase transition there. Okay, so first I would like to say that there is indeed crystals, three-dimensional crystals, which are really described for their magnetic properties by such one-dimensional model. I will give some example a bit later. And such crystals, they can be tested for their magnetic properties by neutron scattering experiments. And so you can really test, for example, in neutron scattering experiments, the scattering data, they are directly related to the two-point correlation functions. So you can really test the dynamics of such Heisenberg chains in such crystals. While there are, of course, the archetype, such chains are archetype of quantum integrable models, and as I said, many of the tools that we use nowadays in more general integrable models have been invented just in this context. Okay, and we know that there are also the place and in fact, with their associated vertex, two-dimensional vertex models where quantum groups appeared. And as I said here, they eventually appear in different situations far from magnetism, which is the topic of this conference. And there is very nice link to combinatorics, also to more mathematical problems in special points. Okay, so let me just say that and give you some examples of really crystals, three-dimensional crystals, which have one-dimensional Heisenberg description and for their magnetic properties. And such an example is provided, for example, by this KCUF3 crystal. And you see in this crystal, let me show the picture, maybe. Yes, it's a crystal like this, and there is various atoms there. And the main effect for magnetism is due to the copper atoms there. And what happens is that there is some quantum mechanical effect, Yann-Teller effect, that distort a little bit the crystal when you are at small but non-zero temperature, which makes this copper atom to move along this direction. And so the orbitals in the transverse plane here, due to this little distortion, they don't recover each other. And so the magnetic exchange terms on the planes here, along this transverse plane, they become very, very weak compared to the magnetic interaction along this direction. And due to that, in fact, the ratio between the magnetic exchange between the transverse plane and the vertical direction is of order of 100. So that's why, in fact, such a material can be described by a one-dimensional system, although it is a three-dimensional crystal. Okay, so let me go on, and just to comment also about some old formula which go back to Van Hove in the 50s. In fact, there is a nice connection between correlation functions in the Heisenberg chain. So here you take simply two-point function depending on distance m and time t. So you have two spin sigma, where alpha and beta could be x, y, or z. H is the Hamiltonian, and so you have to compute, and T, big T is the temperature, so eventually you have to compute such correlation functions. If you are at zero temperature, this quantity drops to just the average value of the same object but in the ground state, psi j. And in fact, there is a nice relation between the structure factor, which is essentially the Fourier transform of the two-point function. So discrete Fourier transform with respect to distance and continuum Fourier transform with respect to time. And the differential cross-section of the neutron scattered by the crystal. And such a relation goes back, in fact, to Schwinger, Van Hove, and such people. So it's very old. But you have a direct connection between such cross-section that you can measure experimentally and the two-point function. Okay, so let me show you now some comparison between some computation that we did from beta ansatz and some measurement for this material KCUF3. So on this picture, let me explain, we represented simply the structure factor. So this Fourier transform with respect to time and distance, so it's a function of momentum and energy, S of Q and omega. So it's a Fourier transform of the dynamical spin-spin correlation function. KCUF3 is essentially described by XXX spin chain. So you see that on this picture, what is represented is simply the value of this function. And the rule is that here there is some scale. When the color is blue, here there is energy, there is a momentum, prescaled from -1 to 1. And the color is just giving the value of the function. Okay? The envelope here is just the envelope inside which you have the eigenstates for the chain, okay, for the spinons. And the value of the function is given by the color. So, for example, blue means the function is 0, and dark brown here, or red, is when the function is maximum. So this is what can be computed, and I will describe how it can be computed a bit later in the talk. This is what can be computed from beta ansatz techniques. This is what is measured in actual neutron scattering experiments. So of course there is some small discrepancy, but essentially when you look at the data, it agrees up to less than 10% error, which are essentially due to experimental error bars, plus of course the fact that in such crystals you don't have only spin 1/2 excitation, but if you go to higher energy, you get very often 3/2 and 5/2 spin excitations. So of course you have some other sources of discrepancies. Okay, so this is quite nice agreements. So let me now go back to theory, and the computation has been done with a number of sites, which is about 500. The number of sites, of course, in the crystal is much larger. So when you compute the correlation function from just beta ansatz, you can show that the correction due to finite size, they go like 1/n. So the error you get just when you compute with such big but small number of sites, like 500 or 1,000, is very small. So in this sense, even if you take such a long chain like 1,000 sites, you already are for the correlation function, not for the beta ansatz, in the deep thermodynamical limit. You know that for 1,000 sites, from spectrum point of view, you are not in the really thermodynamical limit, because the distribution of root goes like the log of the length of the chain. So log 1,000 is 3 essentially. So, but for correlation functions, the error you have is just 1/n. So it's much different. Okay. So it means in particular that when you compute the correlation function like we did using the form factors, each individual form factors and the contribution of each sector in the spectrum will change a lot when you increase the size of the chain. When you go, I don't know, to 10 to the 10, for example. But the total contribution, when you sum up everything, will not change more than like 1 over n. Okay, so let me just, to fix the notations, introduce the XXZ Heisenberg chain. So it's very much like XXX, except this anisotropy delta in the z direction. You can eventually add a magnetic field. It is still integrable. I have to say that all what I will describe here is valid for the chain with periodic boundary conditions. But in fact, recently we succeeded to extend this to open chain, or to chain with various integrable boundary conditions, and in the thermodynamic limit with chain with for semi-half infinite chains. And there is also a big interest in that for condensed matter physics. Okay, so essentially you have nearest neighbor interactions. So you have sigma x, sigma y, sigma z fields here, spin 1/2. And the total dimension of the space of states is 2 to the power m, where m is the length of the chain. Okay. So a little history about correlation functions of such chain. It started, of course, with a free fermion point, which is delta equals 0, with many people. And it was eventually solved after, well, many efforts and years. And from the middle of 80s is the problem of general delta, where you are not equivalent to free fermion point. The first attempts were done by Izergin, Korepin, and collaborators from Leningrad, well, St. Petersburg now, and also using better ansatz. The main problem at that time was, and I will comment a bit more later on that, was that you see, if you look at better ansatz states, they are highly non-local states in terms of sigma fields. And this is really the key problem in computing correlation functions for such model, that you compute eigenstates, and you have to compute average value of local operators into eigenstates, which are highly non-local states. So for general delta, a bit later, there was multiple integral representation obtained first by Jimbo Miwa from some assumptions and structures related to Q-deformed Nizhny-Zamolodchikov equations, and in '99 by our team from algebraic better ansatz. And a lot of developments have been done since 2000, and I will try to review some of this. Okay, so what I mean by correlation function, as I said, is simply the average value of some product of local operators in the sense of trace over the space of state of this product of local operators, weighted by the Boltzmann weight with the Hamiltonian h, and divided by the partition function. And this, of course, boils down at t equals 0, and in the case of spin chains in the disordered regime, where the ground state is unique, you have simply average value in the ground state of these local operators. So why is it so difficult? Well, let's consider a typical correlation function, two-point function, at 0 temperature, where you have simply average value in the ground state of the product of two local operators, say theta 1, theta 2. They are, for example, your spin sigmas in site 1 and in site m, for example. There is two strategies to evaluate, that you can imagine, to evaluate such average value. First strategy is you compute the action of your local operators on the ground state. And you get a new state, omega tilde, which of course is not an eigenstate anymore. And then you calculate the resulting scalar products, omega to omega tilde, and you have your correlation function. Another way to compute it is to insert a sum of complete set of eigenstates between the two operators. So you introduce the identity as a sum over the complete set of eigenstates. And then you are led to compute the one-point functions. But either here or there, the problem that you have to solve, of course, beyond computing exact eigenstates and energy level of the Hamiltonian, which is in principle given by beta ansatz, is to obtain the action of local operators on the eigenstates. And this was a point that was really not solved for many, many years. And that this was the key point to go further into this problem. And then, of course, if you succeed to do that, you have to compute the resulting scalar product, which is not completely trivial, of course. Okay, so two main lines are still on the way. One line is related to Q-vertex operators, Q-deformed kinetic thermological equations, and making use of quantum affine symmetry of the infinite spin chain. So this is done in the infinite volume limit for zero magnetic field and zero temperature. It gives elementary blocks of correlation function and form factors for massive case in terms of multiple integrals, and there was some recent progress towards some more algebraic solution of this Q-deformed kinetic thermological equations. From beta ansatz, I will give some more details in the following. It's valid for finite and infinite chains with magnetic field, with temperature. You can put impurities, you can put in integrable boundaries. You can also compute their elementary blocks, spin-spin, dynamical case, form factors. And essentially what you obtain are determinant representations of the form factors, multiple integral representation for correlation functions, and some other nice formulas that I will try to describe. And some of these results can be extended to, at least for the moment, to one continuum model, which is nonlinear Schrödinger model. But this is still work in progress. Part of it has been published last year. Okay, so let me just give the basics of algebraic beta ansatz. That is a basic tool that we needed to compute correlation functions. So algebraic beta ansatz, which is now quite old, was invented by Faddeevsky and Takhtajian, and essentially you can view it as a construction of a map, highly non-trivial map, from your spin operators, local spin operator, to highly non-local operators, which are in T of lambda, which is a so-called quantum monodromy matrix into this game. So it's a set of 4 operators depending on the continuum parameter, spectral parameter lambda. Those objects are constructed by means of ordered product of 2 by 2 matrices, which are the quantum lax matrices. And these quantum lax matrices they have entries which are simply the sigma operators on site n. So if you take the matrix L into this product in position n, it is just a local, the entries are given as simple function of the spin operators on site n. And the very nice feature of this quantum monodromy matrix is that it satisfies Yang-Baxter algebra. It contains commuting conserved charges, simply the sum A plus D is providing the conserved charges. They are commuting, and they contain the Hamiltonian. And then all the strategy of algebraic beta ansatz is not to diagonalize only the Hamiltonian, but to diagonalize all the set of conserved charges, because they are commuting. So you are looking for eigenstates of T of mu, which is this transfer matrix, for arbitrary value of mu in the form which is simply action of the off-diagonal elements of the monodromy matrix onto some trivial reference state. For example, here for this XXZ spin chain, it's just the state where all spins are up. So this is like crash course on algebraic beta ansatz. So I like to view this as just invention of this map from local fields to these non-local operators, but which creates beta eigenstates. And if you want to compute correlation functions, you need to compute action of local operators onto such to mix the two algebras, namely the Yang-Baxter algebra, which is there for these non-local operators, with the standard SU2 algebra of your spins. And this is highly non-trivial. So one way to solve it is just to be able to invert the map, so to solve the so-called quantum inverse scattering problem, so to reconstruct the local spin operators in terms of the non-local operators that create the beta eigenstates. And we found this solution for the first time in 1998, and it's exceptionally simple solution in the sense that sigma plus, minus, and sigma z, they are given essentially as B, C, and A minus D operators, simply transform on the right and on the left by product of transfer matrices, which are conserved quantities. So if you use this reconstruction plus Yang-Baxter algebra of A, B, C, D, you can get the action of any local operators on any of the eigenstates of your system. And hence, you can attack the problem of correlation functions. Size, yes. Sorry, I did not comment on this. Xi's here are arbitrary inhomogeneities that you can put on each lattice site. In the homogeneous chain, all Xi's are set to be 0, and the formula are still valid, of course. By the way, this is one question maybe I can ask to, and you can think about. I would like to know, in the game of ADS-CFT, what could be the role of such inhomogeneity parameters. You know, in the spin chains, you can add this inhomogeneity. The system is still integrable. You have still Yang-Baxter relation and so on. But you get some additional property, is that Q-deformed Nijmeh-Zamolchikov equation, there are equations for such inhomogeneity parameters. I don't know what would be the role of that for ADS-CFT case. In principle, you are in the homogeneous.
Well, it's not quite true. In QCD, you have open spin chains with inhomogeneities. When you consider quark-gluon-quark operators, you have exactly those.
So you have some inhomogeneities?
Yes.
Okay. And do you use them for something?
Oh, yeah, absolutely.
Okay, good. Sorry, I'm not. So maybe you can tell me in private later. Okay, so, and then the last problem you need to solve is the scalar products. You see, when you act with your local operators on eigenstate, you get a sum of states which are no longer eigenstates. So what you need to compute in the end are scalar products of eigenstates with arbitrary states. And this is given by some very nice formula, where if the set of lambdas here are solution of beta equation and mu are arbitrary parameters, you can compute such scalar products as a ratio of two determinants. Well, these two determinants are very nice. The denominator is just Cauchy determinant, so it's very simple. And the numerator is simply a Jacobian. It's a Jacobian matrix of the partial derivative of eigenvalues of T matrix, which is the matrix of all of transfer matrix, sorry, which is a matrix of all conserved quantities. So those are explicit functions of mu and lambdas. So using all of this, you can compute very easily form factors. Okay, probably I have no time to comment about space of states. Well, maybe let me go. Probably I will not be able to describe all what I wanted to say today, but let me comment on something which maybe I did not describe for long. You see, there is very interesting phenomenon in this due to the inhomogeneities. If inhomogeneities parameters are in generic positions, you can change basis. You can invent a very nice change of basis of the spin chain. So for the Hamiltonian, in the usual XXZ Hamiltonian, it would become completely non-local object, highly non-local object. But this change of basis would simplify drastically the ABCD operators, and in particular, it will transform the spin chain in such a way that all sites will be equivalent. So it means that permutation of sites will become trivial. which is not the case where you are in the usual spin chain. And this change of basis is simply given by the notion of twisting in the quantum group. And there is a special twist that you can construct. We did construct this with José Sanchez de Santos quite long ago now. And in this basis, you can, okay, sorry, I cannot describe all the details, but let me just show you what is the change of, what is doing this change of basis. Let me take the B operator, which is creating the beta eigenstates. If you look at the B operator, and you expand it in terms of local spin operators, you get the following expansion. First, you have a sum from site 1 to n of sigma I minus times some diagonal matrices omega I acting on all sites. Sorry. Then you have another term where you have sigma I minus times sigma j minus sigma k plus sum over ijk times again diagonal matrices acting on all other states or all other sites, and so on. And you have a sum of 2 to the power m such terms. So it's in this sense that B operator, which creates beta eigenstates, is highly non-local operator in terms of sigma. Well, if you go to this basis, which is induced by this Drinfeld twist, you have a huge simplification. So if you consider B tilde, which is simply change of, if f is a change of basis, it's fb, f minus, then you see that, well, first of all, D operator becomes diagonal, and B and C operators, they become quasi-local. So it's, instead of 2 to the power m terms, you get only m terms, where m is the number of sides of your chain. And so only sigma minus, one sigma minus remain, only one, or only one sigma plus for C. And all sides are equivalent. So there is a complete symmetry between the sides. And this basis is very nice, and in fact, it is in this basis that we first realized that quantum inverse problem could be solved. Well, you see that here, if you look at this in this basis, you could imagine that you can invert, you can compute sigma minus in terms of B. Well, after you realize that, you can prove it for arbitrary in the standard basis. I mean, it does not matter. The proof is very simple in the end. But and I have the impression that such a basis could be useful maybe in your context also. Okay. So let me just show you. How long do I have? 5 minutes?
You've got 5 minutes left, yes.
Mm-hmm. Okay. So, well, probably I will just be able to attack the introduction of my talk. Okay. So anyway, so let me show you how you compute matrix elements of local operators. Just one point function. Well, suppose you have a one beta state here, one beta state there, and you want to compute the matrix element of your sigma z operator between two such beta states. Well, then you use a quantum inverse problem, and you write sigma z at site n as a product of transfer matrices, which are just A plus D operators, times A minus D, which represents this sigma z, times again product of transfer matrices. And you see that you are already in a good position because this product, okay, it acts to the left very simply because this is a beta eigenstate. So it's an eigenstate of the transfer matrices. So the action of this gives just, on this state, will give just some number. Similarly, the action of this to the right will just give some number because this is an eigenstate. It's a beta eigenstate. So it's an eigenstate of each of these T operators. So what you are left with is that the matrix element of your sigma z operator at site n between two beta states is just some function phi, which you get by the action of these transfer matrices to the left and to the right here, times just A minus D operator between these two beta states. But then you can use Young-Baxter algebra of ABCD operators to act with this A minus D, for example, to the right. It will produce some sum of states which are no longer beta eigenstates. But here you will keep a beta eigenstate. So by using the scalar product formula, you will be able to compute such a matrix element just as a sum of determinants. And this is the type of determinants that we computed with Jean-Sébastien Coe and Rob Hagmans to get the nice picture that I showed you in the beginning. Okay, well, I don't know how to continue in 4 minutes. So now, if you want to compute arbitrary correlation functions, you can do exactly the same. So if you consider, for example, ground state to ground state average value of some arbitrary product of local operators, e.g. are just elementary matrices, 2x2 matrices that you have. Well, so you can put here sigma plus, sigma minus, or sigma z. They are generated by these. So if you can compute such arbitrary products of local operator, average value of arbitrary product of local operators, you are just computing arbitrary correlation functions. And for such quantities, using the quantum inverse scattering problem solution for this to reconstruct these local operators in terms of ABCD operators, well, we were able to show that such correlation function in the thermodynamical limit are given just by some multiple integrals, where the integrand is given explicitly in terms of explicit function of the lambdas here. And such representation is even valid if you have a magnetic field in the game. And this was giving a complete proof of results and conjecture of Jimbo Miwa and collaborators, and even extended this result to the case of non-zero magnetic field, where the quantum affine symmetry is explicitly broken. So this works also in the integrable situation where you don't have this quantum affine. Well, okay. So I guess that if I want to be in time, I have to jump to the conclusions, which I'm sorry, but let me skip everything. No, sorry. I mean, obviously I was too optimistic for in terms of time. So let me just comment about open problems. Main open problem, and I started with it, is what is the asymptotic behavior of correlation functions, and how we can connect to the conformal field theory from the lattice. This is on the way now. In fact, there is a very nice analysis that we are trying to perform. It involves a lot of mathematics, unfortunately. And in fact, it involves special functions that are just that people are on the way to invent, particular in all these Riemann-Hilbert approach to Fredholm determinants and to asymptotics of Fredholm determinants, and all this is involved there. So fortunately, I cannot show now anything about that. But it's on the way, and I have to say that if you consider, for example, the sigma z correlation function, we know from conformal field theory it should behave for large distances as one part which is 1 over distance squared with some coefficient which is known, plus some oscillating term in terms of distance, like -1 to the power distance, divided by the distance to some fractional power. And this fractional power is depending on the anisotropy, it's depending on the magnetic field, and so on. And these two behavior, these two critical exponents, we have been able to see them now just by resummation of the correlation function from the lattice. So we have seen them, and we are just trying now to prove everything that subleading correction are really subleading, and so on and so forth. I have to say that one other problem which is related to the asymptotic behavior is the problem of field theory. So one possible approach is from the lattice. There is many problems there, like quantum inverse problem for infinite dimensional representations, which we don't know. And probably one very important problem, which is a link to the Baxter Q operator and to the separation of variables method. And in particular, very interesting case is the case of non-compact spin chain, where the representation are not finite dimensional, and there is a lot of interesting work to be done to extend what we did for the compact case here to this non-compact. And of course, there is even more sophisticated model in some sense, and even very important from condensed matter point of view, like Hubbard model, where there is a lot of problems to be solved. In particular, algebraic beta ansatz is not really in a good shape there, and there is still, I think, a lot of things to be understood. And sigma models, again, we know too little about how to put in an integrable, consistent way such models to the lattice and then to quantize them. But this is certainly a very important question. Okay, I stop there. Sorry for having not been able to describe all the material.
Conserved currents in your representations, do they also simplify? When you introduce these non-local representations, when every sites are equivalent and so on, how do all the conserved currents look?
So the conserved charges here, A plus D, they simplify. And they simplify in the following.
You tell what they are.
Yeah.
What's physics of them?
So I can just tell you how they simplify, okay? So they simplify in the following way. So as I said, D operator becomes diagonal in this new basis, but A operator becomes a double sum of sigma sigma times diagonal matrices acting on all other sides. So it's not really, it's not quasi-local, but you see it's a bit non-local, but not too much. So in fact, in this basis, the XXZ spin chain resembles very much the Godin model. It's a basis where it's almost a Godin model, up to some dressing by diagonal action on. So in the Godin model, everything becomes local, right? B and C, they are just sums over the lattice, and it's completely symmetric. And the conserved charges, they are double sums. So here it's the same, except that instead of having just identity, you have dressing by diagonal matrices, which are tensor product on all other sides. So there is simplification.
Okay, thank you very much. I'd like to thank all the speakers. So let's thank them.